The purpose of this video is to expand on the previous normal distribution video. If you remember from that video, we talked about how the normal distribution can be used to understand things that happen in regular day life. The crux of the video is the idea that events tend to follow what are called a normal distribution, meaning that the majority of events are going to fall around the center. These events that we're talking about are generally events that have continuous numbers. So, for example, if we're talking about running a mile, as we did in the last video, there's a lot of times that people could run when they're running a mile. You know, from 4 minutes to, say, 15 or 20 minutes exactly for a mile, you know. So these numbers, we call them continuous numbers, meaning they can be, 4 minutes exactly, or they could be, 4.0001 or 4.156 or 6.623, etc. The normal distribution works extremely well with continuous numbers. Such numbers would be continuous or interval scale numbers. So when we think about the running example, we know that if we forget all about z-charts and normal distributions, and we just think about running, and we think about how some people finished really fast, so that would be like down in this area right here, because that'd be the fastest runners at 4-minute miles or whatever. Some people run kind of slowly, so they would be up here at more like 10, 11, 12, 13, 14 to 16 minutes. But the majority of the people running in this race are going to fall right here in the middle, as we talked about in the previous video. So they fall in the middle section, which means that the frequency of that event occurring is greater in this section than it would be in this section. So to say that again, the frequency or the chances of something occurring in this section right here is going to be greater than for any other section on the normal distribution. So this middle green section I have annotated here roughly accounts for 68% of the normal distribution. Now you can see I've tried to draw in people because it's very important that you understand that this normal distribution, this height point right up here, is higher because it has a greater frequency. So essentially what this is telling us is not just 68%, but it's, if we had 100 people running in the race, we expect 68 people to fall in this middle section. Now, let's talk about the standard deviations and the middle point and what all that means. So this has been a review up to this point. So now we're going to move on and we're going to talk a little bit about the annotations on this normal distribution. So now let's consider this more professionally drawn z-chart here, and let's talk just a little bit about this line I'm going to highlight here in yellow. We refer to this as zeta, or the Z line. And what do these numbers exactly mean? So it's really helpful in understanding normal distributions if you understand that this little guy here in the middle, mu, he's called mu, and he represents the mean of the process, whatever the process is. So the average time it takes to run a mile. So let's, in our case, let's just assume for purposes of demonstration it takes 10 minutes. So mu, right here, is the mean, and in our case, we're going to call that 10 minutes. I'll put in here MIN. Each one of these, -1, +1, those translate to a standard deviation. So a standard deviation looks like this. And we say that in a normal event, so in an event where we have more than 100 occurrences, that's just a good round ballpark figure, we expect 68% of the participants, if assuming it's a continuous number event, to fall in this middle 68%. So what that means, like I was telling you with the running, is that 68% of 100 runners are typically going to run between a 10-minute mile and plus or minus 1 minute, assuming that we have a standard deviation of 1 minute. So note here, I should tell them originally when I explained standard deviation that in this case it's going to be 1 minute. So if we know that on average it takes 10 minutes to run a mile and the standard deviation is 1 minute, we now know that 68% of the population of our sample ought to run our mile between 9 minutes and 11 minutes, because -1 standard deviation is going to put us at 9 minutes, the mean is 10 minutes, and +1 standard deviation, now we're at 11 minutes. So to summarize, 68% of our runners will run a mile in between 9 and 11 minutes. Now, if we want to go out another standard deviation, now we're going to go out to 95.4, and I just before was using 68 just because it's a good round number. It's really 68.2, but we don't need to worry about that at this point. We just need the basic idea. So now we're going to go out 2 standard deviations. So now we're talking about 95.4% of our runners. Let's just say 95% of our runners. So that means 95 out of 100 people ought to run between yet another minute. So now we can say 95% of our runners will run a mile in between 8 and 12 minutes. So now we've dropped back to 2 standard deviations right here, and we're now at 12 minutes and 8 minutes, and we're this section in between here. So that is 95.4%. So a pretty good chunk of the people, if we start at 100 runners, are going to fall between 8 and 12 minute mile. Now we can go out one more standard deviation. That's the 3rd standard deviation. So now we're going to drop to, of course, we're going to subtract 1 minute here and add 1 minute there. So now we can say that 99.7, or mostly everybody, is going to run between 7 and 13 minute miles. Now, this assumes that everything is normal and we have all normal people here that are all kind of average people. You could always find exceptions to this, but generally speaking, if we took 100 people, I bet we'd find most of them fell between 7 and 13 minutes, assuming that I'm right on my mean. Now, let's take a look at this and line it up with this thing we call a Z-chart. A lot of students really struggle with the understanding of the connection between the normal distribution and the Z-chart. So it's my intention, the purpose of this video, is to connect the normal distribution with the Z-chart. So let's put the Z-chart on here. So here we're looking at a normal distribution and a z-chart. This z-chart that you're looking at is a single tail z-chart, so I'll write out here. And the way you know it's single tail is because there's a 0 up here in the corner. So what that means is that because, remember from the previous video that the normal distribution is symmetrical, everything that happens to one side is the same on the other. So the middle, of course, is 0, but this, notice this 34.1%, we can find this if we go right here to 1 standard deviation. Notice those are the same. This is the same as that. Because what this table tells us is the precise measurements between here and here. So let's go back to our running example. And I told you that 68% of the runners are going to fall between the mu, which we said was 10 minutes, and 1 standard deviation, which is 11, and minus 1 standard deviation, which is 9. That means that the distance of a standard deviation in this example is 1 minute. On all the standard deviations in this example, the standard deviation always has the value of 1 minute. Now, this is where it gets confusing. If we switched and we were no longer talking about running and we were talking about points in a basketball game that professional basketball players shoot, now our mean is going to be different and our standard deviation is going to be different. But what is always, always, always going to be the same is this, 34%. So if you take the average score in a basketball game, if you take the top scorers in the NBA, the average is 21 points, roughly. I'm going from memory here. And the standard deviation is 3 points. So now we apply the same logic, but things are going to be a little bit different. Still, it's still going to line up with the z-chart here. We can still say that 68% of the top shooters in the NBA will score between 21 plus 3, 21 minus 3 in any given game. So we could change our table here. So we know on average, the top shooters in the NBA score 21 points per game, plus or minus 3, because I'm telling you that. So we can put that on our little scale here. We put 21 in the middle, and we put 24 here, and 18 here. So now, before, remember, this base was 1 minute, but now it's switched to 3 points. But this up here, this 34%, it's all going to stay the same. It's still 34% on either side. So we can still say 68% of the top scorers in the NBA are going to score between 18 and 24 points in a game. You know, most of the time. There's always extenuating circumstances, but we're saying 68% of the time. We get that from this z-chart right here. Notice 34%. Remember, it's symmetrical. So we can say 68% are going to fall in the middle. Now, we also use this z-chart to calculate the chances of something happening. So let's just say we wanted to know the chances of somebody scoring 25 points or more in an NBA game, these top NBA players. So here we would take 25 and subtract 21 from it, right, which would be 4 points more than the average, and we divide by 3 there. Actually, let's change that to the chances of somebody scoring 24 points in a game, not 25. So it comes out to equal z equals 1, because this is a z calculation. So we take the score we're interested in, we subtract the mean from it, and we divide it by the standard deviation. We're going to get 1. This z equals 1 means we go over here along this Z line, notice that says Z there, it's a little hard to read, and we find 1, and when we find 1, we find 34%. So now what that tells us is the chances of somebody scoring 24 points or more, that's right here. So now is where you have to kind of stop and think. So there is no formula I can tell you here. There is no way you can memorize this. You have to just stop and think about it. So let's talk about this. I am asking you the chances of somebody of scoring 24 points or more. So we go up here to our drawing, and we're going to get rid of all this, make it cleaner here. And what we want to know is the chances of scoring 24 points or more. So that's this, right? We want all of this in a shaded in area. So I told you that the Z value equals 1. So what does that mean? Well, it means that we have a 34% chance of scoring between 24 and 21. That's essentially what this is telling us. So that gives us enough information to derive the answer to our question, which is the chances of scoring 24 points or more. Well, it's just going to be 50%, 0.5, minus 0.34, which equals 16%. But you can also figure this out just by looking at it, right? You can look at this and you can see, oh, well, this is 13.6 plus 2.1 plus 0.01. Pretty darn close to 16%, right? 13, 14, 15, it's like 15.8. Because it's this amount over here, right over here. Now, I could also ask the same thing, but now just change one word, which is chances of scoring 24 points or less. Now, we have the same calculation. Z is still going to equal 1, but now what am I asking you? Well, I'm not asking you for over here. No, let's erase that. I'm asking you for over here, right? Because we want 24 points or less. So that's all the way down to 0. So what is the chances of scoring? 1, 2, 3, 4, 5, all the way up to 24. Well, Z is still 1. That's not going to change. But now we have to have a different logic. So we know that our Z value suggests 34%. Right there, that's what that 1 means. So that means that there's a 34% chance, but we have to add this other 50% over here on, because we're only looking at this chart here is only giving us half of the values because they're symmetrical. So we just take our 34%, so we'll put it down here, 34% plus 50%, oops, typo here, which is 84%. So there's an 84% chance of scoring 24 points or less. Now, it gets more complicated quickly, right? Maybe I don't ask 24. What if I ask 25 or 26 or something like that? So let's go ahead and do the same thing again using, say, 26, because 26 is going to put us sort of in between 2 and 3 standard deviations here, or, excuse me, between 1 and 2 standard deviations. So let's just give that a try. So we do the same exact process, but this time we're going to say 26 minus 21 divided by 3. We get 1.667. So remember I told you it was going to be somewhere in between 1 and 2, so it's going to be like right in here, right? Because it's the number falls between 24 and 27. So it's 1.67 standard deviations shifted to the right there. So if the question is the chances of scoring 26 or more, then we're going to have, we look up 1.667 on the chart here, so 1.6, we go over here to 6 right there. And this gives us the value of 0.4515. So this is telling us that the distance between here and our little dotted line here, that distance right there is roughly 45%. Remember, this is only half, so the chances of scoring 26 points or more are going to be quite low, right? Because it's just this little tiny bit right here of our distribution. So we could guess it's going to be, you know, a little less than half of 13 and a little less, you know, here. But because the normal distribution is not linear, it's always better to use the z-table, because if you just eyeball it, when you get down to these kind of numbers, you'll be a little off. So we can already see this is 45%, so we just take 0.5 and we subtract 0.45, and we get a 0.5 or a 5% chance of scoring, what did I say, 26 or more. Now, if we want to do or less than, we do the same thing. So now we'll change our pen color here back to the pink. So chances of scoring 26 or less, we still get 0.451. We still get this 0.4515, but now our interpretation is going to be different, because now we're talking about not just this 45% here. That's all great. We want to include that. But we also want to include this part over here, our 50%. So now we take 0.5 plus 0.45 and we get 95%. So we could say chances of scoring 26 points or less are going to be about 95%. Because it's right here, 26 is where that's going to fall. It's everything to the left of that value, 26. So I hope that this video explains the connection between this normal distribution curve and this z-chart here. Understanding the more or the less, you have to look at the nuances in the question. There is no standard procedure you can always use. It just doesn't work like that. So I hope this has helped to clarify what can be a very confusing system. And, you know, understanding this is really important because it underlies everything in statistics. So I hope this is helpful.